Beneath the swirling clouds, NASA has discovered something that nobody expected. A planet that is hiding slushy hailstones the size of softballs, lightning in places lightning should not exist, and an entire layer of chemistry quietly hidden from every instrument we have ever pointed at it. This is data transmitted back to Earth by a single solar-powered spacecraft looping around Jupiter for nearly a decade. So, let's go inside. Jupiter has a problem. When Juno arrived and started looking carefully at the atmosphere with an instrument called the microwave radiometer, it found something that did not make sense. Ammonia was missing from most of the atmosphere. As scientists looked deeper, they saw that the amount of ammonia kept changing as you moved down through the planet. There were huge stretches of Jupiter's atmosphere that should have been full of ammonia and were not. Now, there were small clues to this even before Juno. Earlier radio observations from the ground had hinted that ammonia was depleted down to about 50 kilometers below the cloud tops. But Juno revealed that the depletion went much, much deeper, down to around 150 kilometers at nearly every latitude. So, where was it going? The first instinct was rain. Maybe ammonia and water were combining in the upper atmosphere and falling as a kind of slushy precipitation. But the math did not work. Rain alone could not carry ammonia deep enough to explain the observations. The drops would evaporate long before they reached the depths where the ammonia was disappearing. You needed something heavier, something that could fall further. That is when a Juno scientist named Heidi Becker noticed something strange in the data from another instrument. Juno carries a camera called the Stellar Reference Unit. It is sensitive enough to pick up flashes of light on the dark side of Jupiter, and what it had been catching on those close passes over the cloud tops were lightning flashes. Smaller, shallower flashes than anyone expected, originating much higher up in the atmosphere than lightning was supposed to exist on Jupiter. This was a problem, because ever since Voyager first photographed Jovian lightning back in 1979, the assumption had been that Jupiter's lightning was basically like Earth's. It happened in thunderstorms where water existed in all three phases: ice, liquid, and gas. On Jupiter, that placed those storms somewhere between 45 and 65 kilometers below the visible clouds, at temperatures hovering near the freezing point of water. But these new flashes were not coming from down there. They were coming from above the cloud tops, more than 25 kilometers above the water clouds, at altitudes where the temperature drops below -88 degrees Celsius. Far too cold for liquid water to exist on its own. So how could there be lightning? The answer turned out to be ammonia. At those very high, very cold altitudes, ammonia vapor acts like an antifreeze. It lowers the melting point of water ice. So when violent updrafts in Jupiter's storms hurl water ice crystals upward into that region, the ammonia vapor melts them, forming a strange new substance, droplets of ammonia-water liquid that should not, by any normal logic, exist that high in the atmosphere. The droplets collide with the rising ice crystals. The clouds become electrified, and lightning sparks across them. There are no clouds like this on Earth. They are entirely Jovian. This was a beautiful discovery on its own. But what happened next was even better, because as soon as Juno's principal investigator, Scott Bolton, heard about the shallow lightning, he realized it was the missing piece of the ammonia puzzle. If ammonia and water were mixing way up there in the upper atmosphere, then maybe they were not just sparking lightning. Maybe they were forming something that could carry the ammonia down, something heavy, something solid, something that could fall. And that was when the mushballs entered the story. Picture a slushy ball of ammonia and water encased in a hard outer shell of water ice. Picture it growing, layer by layer, inside a violent thunderstorm tens of kilometers above Jupiter's clouds. Picture it as it gets bigger and bigger until eventually it is the size of a softball. And then picture it falling. This is a mushball. The idea was first proposed in 2020 by a Juno co-investigator named Tristan Guillot, working at the Université Côte d'Azur in France. His paper laid out the basic mechanism. Strong updrafts inside Jupiter's biggest storms could fling tiny ice particles high above the clouds. Up there, the ice would meet ammonia vapor and turn into a slushy liquid. As the particle was carried up and down inside the storm, it would grow, just like a hailstone on Earth, layers of water ammonia slush, a thicker outer crust of pure water ice. The whole structure binding water and ammonia together in a ratio of roughly 2 parts water to 1 part ammonia gas. Eventually, the mushball would get heavy enough that the storm could no longer hold it aloft. And then it would fall. Not just back into the cloud deck, but down, deep, hundreds of kilometers into the planet, into warmer and warmer regions, until it eventually evaporated entirely. And the ammonia and water it had been carrying would be released, locked away far below the levels that Juno's instruments could see. That was the theory. But theories on Jupiter are easy to write down. Proving them is the hard part. The mushball idea was, frankly, weird. So weird that even some of the scientists who looked at it most closely did not believe it at first. One of those scientists, named Chris Mokel, initially thought the theory was too elaborate to be real. Too many things had to line up. Too many specific conditions had to be met. Mokel actually said, in his own words, that he basically spent 3 years trying to prove it wrong. He could not prove it wrong. Instead, the more carefully he looked, the more the data lined up with the mushball picture. And in March of 2025, Mokel and his colleagues published a paper in Science Advances confirming that mushball hailstorms appear to actually be happening on Jupiter. A separate preprint, posted to Arxiv in April of 2025, included the first 3-dimensional visualization of Jupiter's upper atmosphere built from data collected by Juno, the Hubble Space Telescope, and the Very Large Array radio telescopes in New Mexico, all combined together. The key piece of evidence was a small, unusual signature in Juno's radio data picked up beneath one storm cloud. It looked like either a region of cooling, meaning ice, was melting, or a region where ammonia was suddenly being released. Either explanation only worked if mushballs were involved. That was what finally convinced Mokel. The journey of a mushball, as it now stands, is one of the strangest weather events in the solar system. It begins around 50 to 60 kilometers below the visible cloud deck, where water droplets first form. A storm's updraft grabs those droplets and lifts them rapidly upward, all the way to the top of the cloud deck, where they freeze. From there, the icy particles get punched even higher into the cold, ammonia-rich layer where the antifreeze chemistry takes over. The slushy mushballs grow as they cycle through the storm, picking up more water and more ammonia until they are too heavy to stay aloft. Then they fall. Past the cloud deck, past the storm that made them, more than 100 kilometers down into the planet, into warmer regions where they finally evaporate, depositing their cargo of water and ammonia at depths no instrument can directly see. So the ammonia is not actually missing from Jupiter. It is just hidden. It was there all along, but it had cloaked itself by mixing with water and quietly riding mushballs into the deep atmosphere. And here is the strangest part. Mokel and DePater believe that this is probably not unique to Jupiter. The same process, the same kind of mushball storm could be happening on Saturn, on Uranus, on Neptune, and on giant gaseous exoplanets around other stars far beyond our own solar system. If that turns out to be true, then mushballs may be one of the most common forms of weather in the entire galaxy. And we only just figured out they were real. There is a temptation, when you look at Jupiter, to assume that what you see on the surface tells you what is going on inside. The clouds are violent. The storms are massive. The Great Red Spot has been raging for centuries. It is hard not to imagine all of that turbulence stirring the entire planet from top to bottom. like a giant boiling pot. But the data is now showing us something very different. When Moeckel and his collaborators built their three-dimensional picture of Jupiter's upper atmosphere, they discovered that most of the weather on Jupiter is actually shallow, surprisingly shallow. The vast majority of the colorful, swirling patterns we associate with the planet, the bands, the eddies, the kaleidoscope of motion, only reach about 10 to 20 kilometers below the visible cloud deck. On a planet with a radius of around 70,000 kilometers, that is essentially a thin skin. In other words, almost everything we see from outside is happening at the very surface of the atmosphere. There are exceptions. A few specific kinds of storms can punch much deeper, hurricane-like vortices, hotspots that are linked to ammonia-rich plumes wrapping around the planet in long, wave-like structures, and the mushball-generating thunderstorms we just talked about. Those are the systems that reach down and actually mix things up. They are what unmix what scientists once assumed was a uniform atmosphere. Moeckel put it simply: the turbulent cloud tops would lead you to believe the atmosphere is well mixed. But just because the top of a pot is boiling does not mean the whole pot is boiling. Below the visible churn, Jupiter's atmosphere is steady, sluggish, far calmer than anyone expected. And that has consequences. For decades, when astronomers looked at giant planets from far away, they had to assume that the chemistry they saw on the surface roughly reflected what was inside. It was the only assumption you could make. But the shallow weather on Jupiter shows that this assumption is not safe. The top of the atmosphere is, in Moeckel's words, a pretty bad representative of what is actually inside the planet. If that is true for Jupiter, it is probably true for the giant exoplanets we keep discovering around distant stars. But the story does not end there. Because around the same time that Moeckel was confirming the mushballs and mapping the shallow storms, another team was attacking the same problem from a completely different angle. This was a study led by Jihyun Yang, a postdoctoral researcher at the University of Chicago, working with scientists at NASA's Jet Propulsion Laboratory. It was published on January 8, 2026, in the Planetary Science Journal. And it tried to do something that had not been done before to model Jupiter's atmosphere by combining chemistry and hydrodynamics together in a single simulation. Now, why does that matter? Jupiter's atmosphere is, chemically, a maze. Molecules are constantly traveling between the extremely hot conditions deep inside the planet and the much cooler conditions higher up. As they move, they shift between phases and rearrange themselves through thousands of different reactions. On top of that, clouds and droplets are forming and dissolving and falling and rising. Earlier studies had usually treated chemistry and atmospheric motion as separate problems, modeling them one at a time. Yang's team wanted to model them together, both at once, a first. What they found supported the picture that Moeckel had been building. The simulation suggested that vertical mixing inside Jupiter's atmosphere happens dramatically more slowly than the standard assumptions had been. According to the model, the diffusion of gases is something like 35 to 40 times slower than scientists had long believed. Instead of a single molecule taking a few hours to move through one layer of the atmosphere, it might take several weeks. Jupiter, in other words, is not a roiling cauldron all the way down. It is a planet with a thin, restless skin and a vast, slow-moving interior beneath it. That changes how we think about how heat moves through the planet. It changes how we think about how storms form. It changes how chemistry plays out at depths we cannot see. And it gives Yang's model the resolution to do something else interesting, make a new estimate of how much oxygen Jupiter actually contains, because almost all of the oxygen on Jupiter is locked up inside water. And water is hidden so deep inside the planet that no spacecraft has ever directly measured it. Here is a question that does not sound dramatic but actually is. How much oxygen is there inside Jupiter? For decades, scientists have been arguing about this. The reason it matters comes down to how planets are built. The elements that make up planets are the same elements that make up the Sunday. Hydrogen, helium, oxygen, carbon, nitrogen, iron, all of it came from the same swirling cloud of material that became the solar system. But the proportions of those elements can vary from planet to planet, and those variations are clues. They are fingerprints. They tell us where a planet formed, how it formed, and what it gathered up along the way. So if you can pin down how much oxygen Jupiter has, you can start to answer one of the biggest open questions in planetary science. Did Jupiter form in the place where it currently orbits, or did it form somewhere else and migrate in over time? The problem, again, is that the oxygen on Jupiter is mostly hidden. It is bound up inside water molecules, and those water molecules condense deep below the visible clouds, far beneath the reach of any spacecraft. The Galileo probe that NASA sent down into Jupiter's atmosphere only sampled the uppermost layers before contact was lost. Juno can probe the gravity field and the magnetic field, but it cannot directly taste the water at the depths where it lives. So for years, different studies came back with wildly different estimates. One major recent study had suggested that Jupiter contained only about a third as much oxygen as the Sunday. Other studies pointed to a much higher number. There was no consensus. This is the question that Yang's combined chemistry and hydrodynamics model was built to attack. By tracking how water vapor, clouds, and chemical reactions interacted as material circulated slowly between the deep, hot layers and the cooler upper regions, the team could reconstruct how oxygen ought to be distributed throughout the planet. The result was a value of about 1.5 times more oxygen than the Sunday. Now, that number does not sound exotic on paper, but it points to something specific about Jupiter's history. It supports formation models in which Jupiter grew early in the solar system's history, by accreting icy material, frozen water, and oxygen-rich solids somewhere near or even beyond what is called the snow line. The snow line is the distance from the sun where it gets cold enough for water to exist as ice. Out there, ice is much easier for a growing planet to scoop up than water vapor. So if Jupiter formed in or near the snow line, it would have naturally absorbed more oxygen than the sun itself ever did. It is a small fact with a big implication. It tells us that Jupiter likely grew up in the colder reaches of the early solar system, and it tells us that the giant planet we know today is, in part, a frozen archive, a record of the icy material that was floating around our young sun more than 4 billion years ago. So Jupiter is not just a planet, it is a time capsule. And for Yang and his team, this is just one example of what happens when you finally model the chemistry and the motion together. As Yang himself put it, it really shows how much we still have to learn about planets, even in our own solar system. Now, there is one more thing Juno has been quietly tracking, and it might be the strangest of all. Most people have heard of the Great Red Spot. It is the famous storm, the one you can see from the outside. The one that has been spinning for centuries. But Jupiter has another spot, one you cannot see. It is invisible to the eye. You would never notice it from a photograph. It only shows up when you measure the planet's magnetic field, and when you do, it appears as an isolated, intense patch of magnetic flux sitting near Jupiter's equator, around 80 degrees west longitude. It is called the Great Blue Spot. Jupiter has the strongest magnetic field of any planet in the solar system. We have known about it since the earliest missions. Pioneer 10 and 11 mapped it. Voyager 1 mapped it. Ulysses mapped it. Each spacecraft added another piece. But it was not until Juno arrived in 2016 with its sensitive magnetometer on its unique pole-to-pole orbit that we could actually generate a detailed three-dimensional model of the field. That model is called JRM-9, and it was built from data collected during Juno's first 8 science passes. When the Juno team compared the new map to all the older measurements going back to Pioneer, they noticed something nobody had ever seen before on another planet. Jupiter's magnetic field had changed, not by a lot. Small, distinct, very subtle changes, but they were definitely there. And the changes had been happening across the entire stretch of time between the Pioneer flybys and the Juno measurements. This phenomenon has a name. It is called secular variation. It is something we have studied for a long time on Earth, the slow, gradual shifting of a planet's magnetic field over decades and centuries. But until Juno, we had never definitively measured it on any other world. The team published the discovery in Nature Astronomy. Scott Bolton, the principal investigator of Juno, said that secular variation had been on the wish list of planetary scientists for decades. It only became possible because of Juno's unusually accurate instruments and its strange looping orbit. But finding the change was only half the story. The next question was, what was driving it? After ruling out other possibilities, the Juno team concluded that the most likely cause was Jupiter's atmospheric winds. Specifically, the deep zonal winds. These are the powerful east-west jet streams that wrap around the planet, and they extend far below the visible cloud tops. They reach down more than 3,000 kilometers to the depth where Jupiter's interior begins changing from a gas into a highly conductive liquid metal. As the winds stretch and shear the magnetic field, they slowly drag it around the planet, distorting it over time. Nowhere is this effect stronger than at the Great Blue Spot. The Great Blue Spot is a localized patch of intense magnetic flux. The strong zonal winds at that latitude tear at it, stretching the field east and west. And, as a result, it is the single biggest source of secular variation on the entire planet. The blue spot is actually drifting eastward at a rate of about 1.5 inches per second relative to the solid body rotation of Jupiter. That sounds slow, but over time, it is enough to lap the entire planet in about 360 years. A Juno scientist named Kime Moore, working at Harvard University, said that one narrow magnetic hotspot, the Great Blue Spot, appears to be responsible for almost all of Jupiter's secular variation. Just one anomaly, drifting silently, century by century, around an entire world. And the discovery does more than just teach us about Jupiter. The same processes that shape the Great Blue Spot may help us understand how Earth's magnetic field changes too. Our own planet's field is full of mysteries we have not yet solved. Watching Jupiter's field shift in real time gives us a kind of natural experiment we have never had before. There is one more region of Jupiter that has been hiding things from us. The poles. When Juno first started flying its low passes over the planet, it sent back images that no spacecraft had ever taken. At the North Pole, it found a single massive cyclone surrounded by 8 smaller cyclones, all arranged in a perfect geometric pattern. Polygons of storms, circling the pole, none of them ever leaving. That is not how cyclones work on Earth. Hurricanes on our planet form in isolation. They drift away from their starting points. They eventually break up before they can reach the pole because they need warm, moist air to survive, and the Coriolis force weakens as you approach the rotation axis. On Jupiter, none of those rules seem to apply. The polar cyclones are confined to the polar region. They cluster together. They have stayed stable for years. By tracking them across multiple Juno orbits, the team noticed something subtle. Each cyclone was slowly drifting toward the pole due to a process called beta drift, the same interaction between the Coriolis force and the storm's circular winds that causes hurricanes to migrate on Earth. But the closer the Jovian cyclones got to the pole, the more they began to interact with each other. Their motion would slow down. They would bump up against their neighbors and bounce off, almost like springs in a mechanical system. Over time, the entire pattern stabilized. The cyclones oscillate around their positions and slowly drift westward, clockwise, around the pole. A Juno co-investigator named Yohai Kaspi, working at the Weizmann Institute of Science in Israel, helped build the model that explains this strange dance. And the same model may eventually help us understand how cyclones move on other planets, including our own. Then there is what Juno's microwave radiometer found in February of 2023, when it began performing a new round of radio occultation experiments. Among the most striking results was the first ever temperature measurement of Jupiter's north polar stratospheric cap. That region of the atmosphere is about 11 degrees Celsius cooler than its surroundings, and it is encircled by winds blowing at over 100 miles per hour. It is a cold patch at the top of the world, ringed by a wind wall. And while Juno was studying Jupiter, it has also been turning some of its instruments toward one of Jupiter's moons, Io. Io is the most volcanically active body in the solar system. The Juno team combined data from the microwave radiometer with infrared imagery from another instrument called GEORAM, the Jovian Infrared Auroral Mapper, and they were surprised by what they saw. Beneath Io's cooled crust, there is evidence of still warm magma that has not yet solidified. At every latitude and longitude, cooling lava flows everywhere. The data suggests that about 10% of Io's surface has these remnants of slowly cooling lava just beneath it. A Juno scientist named Shannon Brown, working at the Jet Propulsion Laboratory, described Io's volcanoes and lava fields and underground flows as functioning a bit like a car radiator. They efficiently move heat from the moon's interior up to the surface, where it can finally be lost to the vacuum of space. GEORAM also identified what may be the most energetic eruption ever recorded in Io's history, first spotted during a flyby on December 27, 2024. The eruption was still spewing lava and ash as recently as March of the following year. Mission scientists believe it remains active, and all of this, the cyclones, the cold cap, the cooling lava on Io, has been happening while Juno has continued its long, looping orbits around Jupiter. Each pass takes the spacecraft to a new vantage point. Each pass adds another piece of the puzzle. Scott Bolton has said, more than once, that one of the great things about Juno is that the orbit is always changing. Each science flyby takes the spacecraft somewhere it has never been before, including, repeatedly, through the strongest planetary radiation belts in the solar system. He has called it a little scary, but Juno was built like a tank, and every time it passes through, it learns more about what is in there. So this is what NASA actually found inside Jupiter. A planet that is smaller than we thought, and more squashed. A planet whose true shape we only recently measured to high precision. A planet with shallow weather sitting on top of a slow, sluggish interior. A planet that hides its ammonia inside slushy hailstones the size of softballs and rains them down through layers of cloud no instrument has ever seen. A planet whose deepest winds shear and stretch a magnetic field so vast that one strange anomaly inside it, the Great Blue Spot, quietly drifts around the entire world over the course of centuries. A planet with cyclones at its poles that bounce off one another like springs. A planet that, according to the latest models, holds about 1.5 times more oxygen than the Sun, suggesting it grew up out near the icy edge of the early solar system and then settled into the orbit we see today. And every one of those discoveries was made within roughly the last decade. What is striking about all of this is not the answers. It is how the answers keep changing the questions. We thought we knew the size of Jupiter. We did not. We thought we knew its atmosphere was well mixed. It is not. We thought we knew where its ammonia went. We were wrong. We thought a planetary magnetic field was static. It turns out it drifts. Each new piece of data reveals one more thing we had been quietly assuming for decades. And each new instrument that arrives at Jupiter seems to find another anomaly that does not fit the picture we had built. There are things we still do not know. We do not know exactly how Jupiter formed, only that its oxygen content points toward an icy origin. We do not know whether its core is sharp or fuzzy, dense or diluted. We do not know whether the slow, sluggish interior we are now starting to model holds even stranger weather we have not yet detected. We do not know whether the mushball storms we have confirmed on Jupiter are also raining down on Saturn or Uranus or Neptune or on giant exoplanets light years away. The evidence suggests they probably are. But we have not seen them yet, and we still cannot directly look at the water layer. The place where all of Jupiter's oxygen is locked up. The place where the ammonia finally evaporates and reveals itself. The place where the mushballs finish their long fall. That layer is still hidden. It is still waiting. What Juno has done is something quieter and more important than any single discovery. It has shown us that Jupiter is not a puzzle with a few missing pieces. It is a puzzle whose pieces keep changing shape every time we look closely. The largest planet in our solar system is also, by a wide margin, the strangest. And after thousands of years of looking at it, we are only just beginning to understand how little of it we actually understand. The clouds keep moving. The storms keep raging. The great blue spot keeps drifting eastward, almost imperceptibly, on its 360-year journey around the equator. The mushballs keep falling. The polar cyclones keep bouncing off each other in their quiet, geometric dance. And somewhere, deep inside all of it, at depths no spacecraft has ever reached, is a planet that we still do not really know. For now, all we can do is keep watching,